Welcome, everyone, to the Critical Power Channel. This is about backup and generation, and what an incredible, perfect timing discussion. We have Keith Maclean-Martin. He's the technical director at Pillar UK Limited. But most important, we're going to be looking today at stabilization and storage solutions for high-performance microgrids. But this is really Pillar's look at future-proofing data centers. What a concept, future-proofing, strategies for AI-driven energy demands. And with that, I've got to say, Keith, thank you so much for the time, because I know you're incredibly busy, and everyone at Pillar's busy. So for this time, much appreciation. Let's get right to it. We've got questions at the end. I hope you've got time for to answer, because folks have a lot of issues, But great topic. Let's get right to it. This is a critical issue now. To you, Keith, thank you, sir, so much.
Oh, thank you, Stephen, for that nice introduction. Yeah, it's a very hot topic at the moment, and let's get straight into it in that case. So, although we're in the early stages of AI era, it's still very apparent that this accelerated growth is potentially exponential right now, even outstripping that of Moore's law for this AI growth. AI's growth of compute power is driving larger and larger data sets to be used. This is the enabler, though, for bringing predictive and machine learning technologies and applications right to the very forefront. In essence, this is the growth of AI at pace. So, with power demands growing and driving this forward, we need to achieve higher and higher levels of data center densities in this space right now. Traditional data centers were achieving rack densities around that of 15 kilowatts, now pushing 40 to 60 kilowatts. AI-ready racks are discussing values which are in excess of 300 kilowatts a rack. The global energy consumption for data centers is predicted to jump from 460 terawatt hours in the 2022 to what's more than now, actually 1,000 terawatt hours come 2026. So AI is therefore posing a significant demand on the energy networks, and this is at great pace, as we see. This is going to impact the design and the operation of the data centers and mission-critical facilities. Just look at the change and advances in cooling technologies. However, it is apparent that power and its availability is becoming mission-critical for data centers, which are now actually part of the UK's national critical infrastructure. The current and future power demands for the global electric grid for AI data centers is therefore very apparent and in the forefront of the press everywhere. Data center operators are facing massive delays in grid connections, anywhere up to sort of 10 years and beyond, to give that availability. Reduction of the issues that we're faced with those connection times is actually being compounded by the changes in the grid. We've got a great reduction in rotating base generation. This is being replaced with renewable sources. This is impacting the stability of the grid and, in fact, the resilience of it. We have a quantum leap of data center build size. 10 years ago, we were only talking about 20 megawatts. Mm-hmm. Now, there's talk of 800 megawatts plus to be ready for the AI, to be capable of AI workloads. There's also a change in the workload profile for AI. We're now seeing sort of great volatility with quick load demand changes and maybe even sort of significant power factor changes, which both the UPS and the infrastructures must be able to adapt to. So the challenges facing power engineers are not only to deliver energy efficient solutions, but also to think differently for alternative and modular power generation schemes. We need to be adaptive based on not only the power demand, but actually what's available there from the grid utility. So data center operator and developers, probably the first question they now need to ask is, what's the local grid like? Where's the power? Can we get it? And this will determine sort of the grid connectivity pathway and the timeline that will follow. So when grid power is available or in just a short term, building data centers the traditional ways is likely to continue at the same speed, driven by the speed to market as the key metric. Although the electrical architecture and the UPS selection will become more critical when actually thinking for AI solutions. However, long or perhaps or longer term delays for the grid power availability That's causing a divergence from traditional data center builds. So we're moving away from standby backup generation to microgrid on-site prime power generation. So based on the grid power availability scenarios, let's take a closer look at the possible solutions for adapting the infrastructure to satisfy AI demands and actually the end client needs that may also dovetail to deliver the 2050 sustainability goals that everyone's striving to achieve too. So when the grid's not available or delayed by a decade or so, this is where new build methods or strategies are causing divergence. So the removal of standby backup generation and moving to the microgrid on-site generation for prime power capabilities. So prime on-site generation will provide localized baseload power for the data center, day one operating in island mode perhaps, and in the future, possibly with a hybrid with the grid if the connection ever comes to fruition. So we now have a paradigm shift. If prime power is now localized in the microgrid and not from the utility supply, then the power quality, the availability, and the resilience of that power is more of a known and guaranteed source. It's all under the operator's control. So traditional UPS systems were deployed to protect loads from utility power quality disturbances and bridge the time for the standby generators to take over by bridging with the energy storage. But if we now have on-site prime power of a great quality, of availability, and the resilience that's known and from a guaranteed source, then the use of UPS in traditional way is now obsolete. So infrastructure needs to evolve to power conditioning and stabilization technologies integrated as part of the on-site generation scheme. That helps to compensate the slow response of gas generation and alternative intermittencies introduced by renewable sources. The ability for perhaps cogeneration or grid services is a possibility and can help sustainability goals. However, taking this a step further, the use of baseload on-site generation enables a forward-thinking, perhaps plan, to look at the adoption of hydrogen-ready engines. With static technologies, they're also having to evolve to the load profile of AI. The AI profile is now really volatile with quick load demand changes, and based on the compute needs, we're seeing a sort of significant varying in power factor. This means that UPS infrastructure needs to be really robust and adaptive and must offer very fast response to these significant load step changes. In addition, with operational efficiency key and paramount, a proactive approach to that management in sync with the AI compute demand is essential. Now, conventional or monolithic static UPSs have fixed capacities and not easily scalable without parallel modules. Typically fixed at sort of 1,000 or 1,200 kilowatt capacities, built up of non-redundant 300 or 400 kilowatt inverter assemblies. Now, with limited flexibility, efficiency optimization versus load demand is typically not possible. So for equivalent sized modular UPS, these are typically made up of 50 or perhaps 100 kilowatt power modules that are easily scalable from the initial stage to the future load demands and can also deploy flexibly to achieve the operating efficiency optimization. Now, traditional data center load profiles were somewhat steady state and only significant step changes introduced during infrastructure failures. However, the AI compute demand actually is facing a more volatile and more frequent load changes caused by the load alone, not by these failure events. And this in turn is actually stressing static UPS components more. The use of modular UPS has that advantage of low mean time to repairs, with all module assemblies being hot swappable. Therefore, a robust but also adaptive UPS system is therefore preferable to meet those AI demands. So what is this operational efficiency, this efficiency optimization? Well, If we're looking at a simple 1,000 kilowatt modular static UPS with a load deployed of only 300 kilowatts, where conventional technologies would deploy all power modules operating at 30% load, we can reduce that and optimize the efficiency and deploy only 3 of those power modules to meet the low demand now. This has the effect of optimizing that efficiency, and it can easily be tailored ultimately to achieve N+1 or perhaps N+2 redundancies just at the UPS level to protect and deliver robust responses to those load changes. So if a grid power is available, or perhaps they're there in the short term, that the traditional data center build model is probably still favored. New trends could be considered, such as the removal of the traditional diesel generators by standby natural gas gensets instead. These could be deployed for prime capacities, so deployed when the grid's not available, or actually longer term options for peaker applications when the grid carbon intensities are high. The ability to do this code generation and do alternative grid services offers some sustainability goals, perhaps for clients, but ultimately it can help you to adapt with some renewable sources and a diverse energy portfolio as well. Ultimately, though, the electrical infrastructure is pretty much a known entity. When we've got the utility, we've got the generators, we've got traditional transfer schemes, with UPSs deployed to protect the IT networks and mechanical loads, all supported by system configurations which are typically sort of distributed redundant. Now, what we mustn't forget is that the Uptime Institute is the latest Tier 4 classification for on-site power generation. Means data centers actually need to be rated for prime power delivery. That's even more important because while conventional diesel generators offer data center continuous rating, that's for a very stable load profile. So if we're seeing this dynamic change in these load steps caused by AI workloads, that might mean the reclassification of those generators now. Refreshingly, though, so today's microgrid community shows collaboration with many solutions that are striving to accelerate the road to 2050. And for this discussion, we're going to highlight the solution that we call the Power of 10, which would adopt modular on-site prime power generation using integrated power conditioning and switching technologies. So the goal of sort of achieving 2050 net zero emissions requires significant reductions in renewable fossil fuels and replaced by renewable generation. If you're going to hit the 1.5 degree scenario, demands that 90% of the electricity produced must be renewable by 2050. So the goal is very apparent, and to achieve net zero power production as fast and as effective as possible, this has got to be at the forefront of our thinking and the drive for it. We therefore need to optimize generation and infrastructure needs to be deployed that enables both an evolution to the greener fuels like hydrogen, as well as meeting the demands of the growing power demands called upon by AI today. So the Power of 10 concepts takes the baseload or prime natural gas generation infrastructure and deploys this on-site at the local level. So we've got multiple 10 megawatt medium speed gas engines, modularly deployed and scalable to create hundreds of megawatts of power. The medium speed engines are very good at baseload prime generation because they offer higher efficiencies, lower operating costs and service life, much longer service lives. This eliminates traditional standby diesel generators from the systems and offers full flexibility with renewable generation sources. In addition, this infrastructure is evolvable to greener fuels like hydrogen. The Bergen engine's already running with 25% blended mix of hydrogen, and the goal is to achieve 100% in the very near term. The integrated power conditioning and switching technology, this is coupled to the primary on-site power generation and any other renewable sources there as well. Here we see what is a pillar 2.5 megawatt power conditioning module with a 60 megajoule kinetic energy store. So conditioned power can be distributed as required and scaled to the modular on-site power generation scheme. And the two schemes don't have to match each other's capacity, in fact. So gas gensets and renewable energy sources typically have very slow responses to load demand changes. So frequency stabilization is achieved here with a regulated source and sink of active power compensation for rapid changes in balance between the supply and the demand of this microgrid network, delivering a stable frequency into that space. Voltage compensation is also achieved for dynamic shift in reactive power demand that could otherwise cause a significant voltage sag or surge on the microgrid. So the key to fully flexible power conditioning and stabilization is the bidirectional power flow technology that sits within the stabilization technology. This allows an equal amount of energy to be absorbed or delivered via the kinetic energy store. This reacts to both power deficits and an excess of power as the supply and demand in the microgrid changes. So we've actually got a case study and have done with a semiconductor fab plant for quite some time. This client wanted a grid connection with on-site cogeneration, and that was to utilize combined heat and power sources, optimizing their overall efficiency. The big problem they had, though, was that the quality of the connected grid was very poor and was transferring through to the sensitive tools and causing an impact on the yield and the production. Similarly, in island mode operation, the gas gensets were very unstable, again transmitting the poor quality to the sensitive loads. The solution that we deployed here was to couple an integrated power conditioning and switching technology between the grid and the on-site generation. This prevented the passage of poor quality issues passing between the grid and the critical loads on site. Effectively, what this creates is a microgrid that's connected to a conventional grid quality bus with its own localized, very high quality bus to deliver pure high quality power. In summary, we have a paradigm shift here. For the Power of 10 offers modular and scalable deployment of the Bergen 10 megawatt medium speed gas engines for the prime power coupled with our integrated power conditioning and switching technologies. This provides guaranteed power availability and fully flexible power conditioning to ensure high power quality for AI data centers and their load demand changes. Although we need to think differently for data center builds, the solution is actually not new. This is a quick example of what we see in those two different voltage grid quality buses and the high quality bus that we see on site. This is a case study that's now being renewed and refreshed for the client and deployed with new pillar equipment and upgraded and updated hydrogen-ready gensets too. So in conclusion, I think AI is posing a significant demand to the energy networks, and it's at great pace. This is going to impact the design of solutions throughout the network and present challenges to the engineers to offer alternative and modular power generation solutions. Grid connectivity pathways are diverging data center build plans from traditional data center builds, moving away from traditional standby backup generation to microgrid on-site generation with prime power capabilities. This is causing a paradigm shift, adapting power quality infrastructure according for power conditioning and stabilization with the removal of UPS conventionally. Hyperscalers will expedite microgrid evolution and growth, driven by this mass adoption and thirst for AI power. So to sustain this growth and advancement, it's essential to future-proof data centers and evolve strategies to align with AI, moving forward with resilient microgrid technologies. Thank you. And perhaps back to you, Stephen, in that case.
Wow, thank you very much, Keith. I've got to say, nothing protects quite like Pillar. Now you need you the most Wow. And I also got to say, scaling to AI demands, what a beautiful way that you presented this, because we're all dealing with this now. I got to say, Keith, we got a couple of questions that have already come in. I'm going to remind folks, get those questions in, and don't worry. You can, Keith and his entire team is going to look at it. But Keith, right up front, you mentioned this when you were actually talking about sustainability goals and issues in the grid. What do people mean by grid constraint? And how does that impact the power? Because you're seeing this around the world. You're a pillar. This is what you do.
Very much so. Power is our game, certainly. So with grid constraints, we're seeing this is a number of factors. A lot of the time, we've got diverse geographical locations around a country, a region, a nation that have lots of renewable generation, have lots of generation sources. But they're typically not actually where the real power is actually needed. So one of the constraints we've got around the grid is actually getting power to where it's really needed. That's causing one issue that is causing the national grid to try and introduce new large interconnects, taking mass renewable energy from Scotland in the UK and trying to pump it down to the southeast, where we've got lots and lots of high power data centers due to come online and hungry for power, let's say. The other side of the constraint is that while we're looking at adopting alternative technologies, actually getting a power connection has limitations on the package substations that they're being fed from. This is obviously driving the data center operators to connect higher and higher and higher in the network, going from typically what would have been an 11 kV connection in the UK up to 33, 66, or even a 132 kV connection. So we're pushing up to higher and higher voltage levels in order to get those connections. With that, we've got a kind of a twofold impact from upgrades that are going on with the grid, as well as this thirst for additional power into the network. So pulling more power introduces the potential risk of more fault in feed to the supply point. In turn, as we increase and upgrade the infrastructure, in order to transmit more power around the region and around the space geographically, they're adding and adapting their infrastructure, which is causing them to actually introduce even more fault current, which is now posing the risk that until we get the point of the high voltage infrastructure being upgraded, as well as the lower high voltage levels upgraded, we're in this bottleneck or constraint point. That means that you can't get any more power, even if there might be some availability, because the risk is at the connection point, we might blow up the switchgear, in truth.
True, very true. We're gonna have these problems, and you're right. Big other question that's come in is around you're adding embedded generation. No data center wants to be a utility. We're scared enough. We're risk averse. Come on, Keith. What issues does this present? We've spent so much money on this before. Now you're offering some new solutions, which are great. I love the power of 10. But what is it? How does this change the present grid with this embedded generation?
Well, again, it's a similar issue that we've got. Coming back to the issues around fault current, if you embed additional generation, you now actually impose even more fault current when you run those generators in parallel with the grid. So if you're trying to deploy a conventional microgrid solution where you run gas generators locally on site and power that with the grid to stabilize your generation, now you may only get the ability to parallel one or maybe two generators from your connection point. The introduction of the integrated power conditioning and switching technology upstream of all the on-site generation overcomes that constraint. It fault limits. It ties that site down to a much smaller number in terms of fault impact. Therefore, through what could be potentially a 20 megawatt connection, there's no limits onto what you could actually power onto the site. You could put 100, 200 megawatts of generation on the site without impacting that connection point. Now, the operation of this, there's no significant differences to that of the operation of standby generators. But this time, they're actually using the asset that they've invested significant money on, and now they're taking control of their own destiny. They've got that in their own bag to deliver and look after.
Wow. I mean, truly enhancing microgrid performance and data center performance through the power is genius. And they don't have to become a utility. I love this. Look, I'm so sorry, Keith. We're actually running out of time and they're getting after me. But I got to say to you and to Keith, to you and to everybody at Pillar, thank you so much. But I got to say, could you finally give us your final thoughts, your final word here? Because you're talking to so many great customers around the world, and you've got insight we need right now as we're dealing with this. So, final thoughts, final ideas that we need to consider here, Keith, please, sir?
Thanks, Stephen. I think what we need to think is there are traditional schemes that we deliver, and they're very efficient and very good at supporting the data centers. They're very reliable. But as the network evolves, as data center workloads evolve, as we move to AI infrastructures, what we've done previously, we're seeing has to be evolved, has to be changed. Traditional solutions won't be the right fix for everything. Certainly in the long term, we have to see alternative ways of doing this power generation and integration of stable, high-quality power into the data centers, and deploying mass standby generation with excess UPS capacities into a facility isn't necessarily the right way to go about this in the long term, especially when we don't have any of the power needs and power capacities available in the short term. What we need to look at is opening up our eyes to different schemes and adopting proven technologies in other sectors to actually overcome the challenges that we're facing right now. And currently as an industry, we're screaming out for new solutions that will deliver the power that we need and this AI at growth and pace.
Incredible. And I'm going to repeat something you said, Keith, right near the end. This is new. Oh, sorry. This is new to the data center market. I'm sorry, I did it myself. I'm so excited about it. This is new to the data center market, but not to Pillar.
Correct. We've been doing this for nearly 30 years now. This is schemes that have been running for 30 years and proven in high quality, precision production process engineering for semiconductor fabrication.
Thank you. I mean, going to the expert is critical here. And I'm going to say to everybody, get those questions in. Thank you, Keith, so much for your time into Pillar. Just what you have done is needed right now. And I'm going to say to folks, reach out to Pillar, get those resources, get in additional questions. Please remember this entire episode is on demand and you can send it out to your friends and colleagues. And also, please remember reach out to Pillar. You've been doing this for 30 years. We need your help now. Now is the time when such a great company can support what we're dealing with when you talked about scaling to the AI demand. And with that, I'm going to say, folks, to Pillar and to everybody, Keith, thank you so much. And folks, don't forget, tune in at the top of the hour for the next episode. To Keith, you, and to everybody at Pillar, thanks. We need this now.
Thanks, Stephen.